Right, I was asked to explain question 14 from exercise 8D, so I'm going to do this on Desmos, so hopefully that might help a little bit, especially if you're graphically minded. So we've got the question here. If we read it out, the curve C has parametric equations x equals sine t, y equals cos 2t plus 1, t is between 0 and 2 pi, and we're given that y line y equals k, where k is constant, intersects the curve. And what we're asked to begin with to show that our k is between 0 and 2. So we've got two y equals here. We've got y equals cos 2t plus 1, but we've also got y equals k. As it happens, y equals cos 2t plus 1 looks like this. If you think about what y equals cos t looks like, let's just get this down to brackets. Y equals cos t is our standard cosine graph. I know we've got x here, but if we did that in terms of t, we just envisioned it was t on the x-axis. This is what y equals cos t would look like. If I make it 2t, then you could think about what that's going to look like. Well done if you decided it's going to look like that. It's going to be stretched by a factor of a half on parallel to the x-axis, so effectively squashed in by a factor of 2. And what's going to happen if I add 1 to this? It's going to move up by 1. So I'll translate vertically upwards by 1. So that's what our y equals cos 2t plus 1 looks like. What's our y equals k going to look like? I was really hoping the slide would come up there. Let's try this. Nope. Okay. So y equals some value k, which it's decided to make x for whatever reason. Y is equal to some value anyway. And we have to find out if it was y equals 3. We can actually see graphically that this wouldn't work, as it's not going to intersect with the curve, and we're told that these do intersect. Same with -1, we can see it doesn't intersect, but we can see that it could be 0.5, for example, because we can see it does intersect the curve here and here and here and here and so on. We were of course told that a domain for these, so perhaps it's worth just bearing in mind that domain, that our t is between 0 and 2 pi. Okay. So we can see that it would work if it was 0.5, and we can see graphically it would work between 0 and 2, but of course you don't have graphics software, you certainly won't have graphics software in an exam, so how would you solve this without having graphics software in front of you? Well, you would have to say that if you substitute y equals cos 2t plus 1 into y equals k, then we're going to get that cos 2t plus 1 is equal to k, and cos 2t therefore must be equal to k minus 1. Now then we've got since cos 2t is between -1 and 1, and that is just something you should know. You should know that the range of your trigonometric functions, your sine and your cosine, goes between -1 and +1, and that just means that from your substitution you've got cos 2t is equal to k minus 1, so k minus 1 must be less than or equal to 1 and greater than or equal to -1. Adding 1 to both sides, you get that your k is between 0 and 2. So that's the first part of the question. For the second part of the question, show that the line y equals k is a tangent to the curve. So show that if the line y equals k is a tangent to the curve, then k equals 2. Right, as a rule of thumb for parametric equations, if you are in doubt, then just try and create a Cartesian equation. And that's what we do. So if we knew that y is equal to cos 2t plus 1, that's equal to 1 minus 2 sine squared t plus 1. Now you might be thinking, where does this 1 minus 2 sine squared t plus 1 come from? And it comes from your double angle formulae. So you might remember back to the addition rule. We can get this up. Now we're back to the addition rule, that if you had a cos, let's just double check the question. If you had a cos A plus B, then that is equal to cos A cos B minus sine A sine B. That's how that's one of the addition formulae that we looked at to begin with, and of course that means if cos 2a, so if I made a equal to b, we're going to get cos a times cos a, which is cos squared a minus sine squared a, and then we can use that 1 sine squared plus cos squared is equal to 1 to say that this is also equivalent to 2 cos squared a minus 1. Just like it's equivalent to 1 minus 2 sine squared a as well. So if you're struggling with where that comes from, then it's you just need to remember your addition formulae, and especially a double angle formulae. So if we go back to the question, so that's where 1 minus 2 sine squared t comes from, plus 1, so I get that's equal to 2 minus 2 sine squared t. Since x is equal to sine t, that means we can create our Cartesian equation. We were aiming towards something which had just sine t in it, because that was our expression for x. So that means that our y is equal to 2 minus 2x squared, and we actually have that Cartesian equation here. Right. If y equals k is a... Right, so what we've got to do next, if we substitute our y equals k into this Cartesian equation, instead of our y we can write k, so k would be equal to 2 minus 2x squared. Substituting that in, if y equals k is a tangent to the curve, then it touches the curve at one point. So the discriminant of the quadratic is 0. Alright, so what does this all mean? We've substituted our k in, and then we've remembered if it's a tangent there's only one point of intersection, and we know from the discriminant of a quadratic that if there is only one root of that quadratic, its discriminant is equal to 0. So if we figure out our b squared minus 4ac equaling 0, work through to find out what k would be, and find that it's just when it's 2, then it must be that the only point where that touches is when k is equal to 2. Right, and that's what we do, and that's the end of that solution there. So if I've glossed over anything that makes that difficult to understand, do let me know. I hope that helps.